All right. I am now online. How y'all doing this morning? No, 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 no. I know last night was a party night. Everybody went out partying. Who went partying last night? All right, who is afraid to admit it? Who just likes handing up your hands? All right, there we go. All right, so good morning. By the way, this is going to be an audience participation portion of the day. So I'm going to ask things and you're going to laugh. That's the way it works. My name is J Metz. I am the chair of the Ultra Ethernet Consortium. And I think I may have the wrong slides up here, but we'll make it through. We'll kind of work our way through it. All right, but my colleague Uri and I did a presentation yesterday on the Ultra Ethernet, and I'm going to be talking to you a little bit about today. So have you heard of Ultra Ethernet? I mean, it was on every keynote. I mean, hopefully, yeah, okay. So have you gotten stickers for Ultra Ethernet? I don't get it either. I'm not a sticker person, right? If I had a sticker on my laptop for every time somebody offered me a sticker, I'd have a 10-pound laptop. And it's a Mac, so it's already 9 pounds. So what we're going to be talking about today is an introduction of the Ultra Ethernet Consortium, and we're going to talk a little bit about why we're doing what we're doing and what we're doing what we're doing. So if you've already been familiar with this, you've heard them talk about Ultra Ethernet, the UEC Consortium, and it's been on everybody's keynote. It's a big deal for a lot of different companies. As a matter of fact, there's more than 100 different companies. As the fastest growing organization in the Linux Foundation history, we've gone from 10 companies to 100 companies in less than a year. It's incredible. Right? We have a lot of different companies who are looking to try to provide an Ethernet-based open ecosystem for AI and HPC workloads. Okay, so what does that actually mean? That sounds like a lot of marketing garbage. But in reality, oh yeah, he's nodding his head, yep, yes it does. Sounds like marketing garbage. So let me explain what I mean by that. One of the things that we like about Ethernet is the fact that it is incredibly flexible. It is a great general purpose network. Right? It does an awful lot of things for a lot of different types of workloads. You can do east-west, you can do north-south, you can do storage, you can do a lot of different types of things with Ethernet. The problem is that it's so generalized that if you have a specific workload, making sure that each and every one of those layers is tuned is something of a problem. Right? If you want to get the physical layer to connect to the link layer, if you want to get the link, the knee bone connects to the hip bone, right? If you want to do that, it actually takes quite a bit of work. And so what we've at the Ultra Ethernet Consortium are trying to do is make sure that that synchronization that goes across all of the different layers is tuned to a particular workload. So we have taken the standard Ethernet from the physical layer up into the transport layer and above, and we've made some tweaks up and down the stack to be able to handle different types of workloads, including AI and HPC. Now, AI and HPC have some similarities, but they're not 100% completely the same. And when you start to dig deep into the way into where these workloads actually function, you start to realize that you need to have different types of approaches to having reliability, orderability, flexibility, multipathing, and those kinds of things. So we need to be able to tweak these things up and down the stack. So that's what we're doing at Ultra Ethernet. At the same time, you want to make sure that it actually works up and down the stack. So we created 4 additional work groups that are designed to get the checks and balances and the accountability for this. And we've got compliance, testing, performance, debug, storage, management, to make sure that all of these different horizontal layers are actually working in concert. So it's an incredibly ambitious project. And as a result, we have, to my surprise, as the chair of Ultra Ethernet, found that we're not the only ones that want this to be solved. Right? We've got over 100 different companies now. It just recently passed over the 100 mark. And we've got over 1,400 people who have actually sit into the meetings and contribute. It is an incredibly robust and diverse group of people from all over the planet. So we've got people from the United States, from EMEA, from APAC. It's incredible. So let's take a quick example of what it is that we're actually doing. Generally speaking, when you have an enterprise data center and you're using Ethernet, oh, I like the cameras. Oh, okay, now the cameras come out. All right, great. Jerks. Okay, everybody is a comic. All right, so you have your general purpose network, right? But when you're talking about a specific type of workload, you want to make sure that the network actually winds up doing what you want it to do. So you have back-end networks for your AI and HPC workloads. And then you have a third network, a third type of back-end network if you want to do kind of scale up. What's the difference between scale up and scale out? Well, generally, in a very high-level view, the difference between scale up and scale out is that if I've got these accelerators, GPUs, and I need to connect them together, I need to make sure that the memory regions for the GPUs all act as one huge honking GPU. I got one GPU here, another GPU here, another GPU here, and I'm going to scale this up so that it all looks like one GPU to do all the same work. That's called scale up. If I want to connect this big, huge honking GPU, logical GPU, to other huge honking logical GPUs, I'm going to scale out so that I can do a number of these. UEC is focusing right now on the scale out problem, right? And it's a difficult problem. The reason why it's a difficult problem is because of the fact that every single time you start adding into these additional nodes, you lose just a little bit of efficiency. So the scaling of the network as you grow becomes less and less efficient. Why? Because of the fact that the errors that naturally occur inside of a network wind up being something of a problem. And they compound over time. Well, what we're looking to do is solve the problem for not just 100 nodes, not just 10,000 nodes, not just 100,000 nodes, but 1 million nodes or more. Why do we do that? Because we need to. If you've taken a look at the way that the AI models are working right now, we're talking 1 trillion, 2 trillion, 10 trillion parameter models, which all require an enormous amount of memory that just don't fit into a single GPU. Those GPUs have to communicate with each other and they have to do it over a network. That's what UEC is looking to solve. So when we start looking at the types of workloads, and this is actually kind of critical, when you start looking at the types of workloads, not everything belongs inside of a GPU. Not everything belongs inside of a CPU. And even though you're running some of the same processes and some of the same problems, some of these things are better done inside of CPUs and some of them are done inside of GPUs, which means that the networks can't be 100% exactly the same. You have to tune them for one, you have to tune them for the other. It's very important that you make sure that you get it right because the workload expands over weeks, months, even years for an entire epoch. Right? This is one of those things that we have to keep in mind is that we want to make sure that the network itself behaves the way we want to for the actual workload itself that we're trying to accomplish. So, what does this mean? At the same time as the fact that we have these differences, we also have some similarities. Okay? One of the things that both AI and HPC need is massive scale, like massive scale. Right? We're already talking about more than 100,000 nodes. We're already talking about hundreds of thousands of devices. We're talking about pods that have to communicate. It's a very difficult problem. So the scale winds up being an issue. But when you have these networks that have to communicate, the way that the packets actually traverse across the network becomes something of an issue. Right? You have multiple different ways. I mean, how many people are networking people? Okay? How many people have ever developed a torus topology? All right, I'm impressed. Most people actually can't spell torus, so that's a good sign, okay? So if you've ever cabled up a torus topology, anything greater than 3 dimensions, you know how much of a pain in the butt it is, right? But the reason why we do that, the reason why we go through that pain is because the actual topology matters for the workload, right? So when we start to talk about this, we need to make sure that we have the proper pathing that goes along with it. So being able to understand what the pathing is from each of the endpoints makes a huge difference. What about the ordering? Well, some technologies are very strict about what kind of ordering is. Does it have to be in order or can it be reassembled at the end? Some cases yes, some cases no. So you need to have the flexibility. Ultra Ethernet actually takes that work and says this particular workload and that particular workload, that one needs to be strictly ordered and that one does not. I want to run both of them at the same time on the same network. UEC allows you to do that. So in order to be able to do this at massive scale, you have to be able to be very concerned about congestion, right? Because the congestion is one of those things that is absolutely a pain in the butt when you want to make sure that these workloads actually work in the most efficient center. So you have to have more efficient congestion control. This is why I'm drinking some coffee, by the way. Blah, blah, blah. All right. So we've got modernized both sender and receiver-based congestion control, congestion and signaling, and optimized telemetry that goes along with both of those. So ultimately, at the end of the day, we've also we want to make sure that everything is built in with security. So we've got a stack that actually goes through a security layer every single time, but it's optional because not all workloads require that same level of security. But if you want it, it's built in, okay? So ultimately, at the end of the day, we want to make sure that, and for those of you who know Silvano, at the end of the day, you want to make absolutely sure that you have the lowest of tail latency and incredibly high efficiency on the bandwidth. And there's a whole bunch of stuff. All right, so let me go through a little bit about what this is. So if you're really curious about the technical details, I'll go through as much as I possibly can. Let me just explain how this kind of works. Let's assume that you've got these different kinds of workloads, and if you take a look at an AI workload, for example, a training workload, there are many, many, many steps inside of it. You have forward passes and you have backward passes. You have the communication that goes from the GPU into the CPU and back again. The kinds of work to generate a token is non-trivial. There's a lot of back and forth of the data that has to move. All right. Most people don't think about this. They think about, well, I've got training, I've got inference, and then that's as far as they go. But inside of an AI training environment, you've got a lot of movement of data that has to go back and forth between the different endpoints. Some of those workloads inside of an AI, some of those tasks inside of an AI workload, some of them require ordering, some of them require reliability, some of them do not. Some of them are control plane traffic, some of them are management traffic, but they're all important. They all have to be. So the way the Ultra Ethernet works is we create a semantic layer in particular to create an idea of how that packet is supposed to be transmitted. We identify a reliability, we identify the ordering, we transfer the memory region, and we build that into each packet. What does that give us? That gives us incredible amounts of flexibility. We can say this packet can go that way, this packet of the same message and the same transaction can go that way. We get the signaling that comes back to the sender that says, hey, this is a congestion network, and I can now go into I can automatically and dynamically choose my paths based upon the feedback that I get from the network itself to get to the endpoint and maintain the consistency, and then I drop the connection. It is a completely ephemeral connection for each transaction that we make. This is what allows us to give the scale that we need. We don't set up state. We don't put state across all the different devices. We don't have to record tables in either the switches or inside of the endpoints. It is an incredibly flexible and scalable system. Then what we do is we go all the way down into the stack and we say, hey, look, let's try to make sure that we have the proper reliability at each layer. So we've got extra additional reliability inside of the link layer. We have extra reliability inside the physical layer. So right now, the physical layer and the link layer, they don't talk. In Ultra Ethernet, we take some of the standardized IEEE measurements and we say those optional tags that are going to be made on the physical layer can be read by the link layer, and then we can actually have error correction at the physical layer to make greater reliability and good put at that level to be able to avoid the cascading function that goes up the stack. So that tuning that goes from the physical layer all the way up into the software layer is consistent based upon each workload. So we build upon the shoulders of giants, and then we make a couple tweaks to make the tuning of the workloads work. So to that end, we're trying to make sure that we have the appropriate opportunity to give the workloads the justice that they need for the scales that we're talking about. We're already talking about a number of workloads that require their own nuclear power plants. So if you're going to do that, you're going to have a network that is able to accommodate those things. So we're looking to be able to have all the opportunity that we can to make sure that we're building a system that can grow and scale over time, just like the workloads themselves. Because if we just use a typical bog standard network, we're going to find ourselves at essentially a capability ceiling, which is not what we want. We want to have the network grow along with the requirements for those particular models. And that's exactly what we're looking to accomplish. So I'd like to just finish off really quickly by saying we are in the final stages of the technical stability of the standard. So the way, if you've never been involved in standards, then I highly recommend that you don't. The way that it works is that something that's technically stable then goes through a series of processes before it gets actually published. So we're at the final stages of technical stability. We anticipate that it's going to be completed by the end of this year. The first products have actually been announced already. You've probably seen a couple of them here at the show. And then we're going to see the publication of the specification in the first quarter of next year. And then after that, you're going to see additional functionality for performance, for compliance tests, for storage, for management, and additional functionality coming out later. So on the ultraethernet.org website, you can see some white papers, and I'll go ahead and stand out of the way so you can take pictures, and I'm out of time. But I wanted to thank you very, very much for your patience and coming in on a Thursday morning. Really grateful for the fact that you were very patient and you laughed at my terrible jokes. Again, my name is J Metz. I'm the chair of Ultra Ethernet. There are stickers right behind you if you want them.